Okay, in this second video on rational functions, we're going to define what a rational function is that's not a toolbox function. We're going to find the intercepts, asymptotes, and holes. We're going to be given an equation. We're going to be able to sketch a graph without Desmos or any kind of graphing utility. We're going to be able to write a function from a graph, and we're going to discuss these asymptotes again, vertical and horizontal, and oblique, which is something new in this section. So this part of rational functions, we're going to be doing these items. So let's start off with a definition. Okay, so the definition of a rational function is a function where we have a p of x function and a q of x function divided, and those two functions are going to be polynomial functions. So I've given you some examples here. Here's a linear function over a linear function. Okay, so that's a rational function. Here's a quadratic function over a quadratic function. That's also rational function. And here's a quadratic over a linear, and that's going to be a rational function as well. So we're going to look at those three specific ones in terms of the properties of a rational function. So let's look at asymptotes first. Okay, so vertical asymptotes are when the denominator equals 0 after we factor and reduce anything that we can in the problem. If we get a factor that's reduced out of the function, then that's where a hole is going to occur in the graph. So we're not going to get a vertical asymptote every time if we can reduce the factors. All right, so let's go through and just do vertical asymptotes in this, and then we'll come back and do horizontal. So vertical, this one's factored already. So if we look at this one specifically, what we would do is we would say we'd look at our denominator, x plus 1. So this is vertical. We want to know when it's 0, so x equals -1. We're going to say that's our vertical asymptote on this problem. Okay, let's look at the second one that we have here. So this one we're going to have to factor. Okay, we can't just look at this and say I know where that occurs, or this, because I'm going to need to factor and see if I can reduce. So if I do that, this one on the bottom factors into x plus 2 and x minus 2, because we don't have a middle term, so we want the middles to drop out of the multiplication. And this one we have x and x for x squared, and 6, we can either have 6 and 1 or we can have 3 and 2. Well, we want the middle term to be -1, so we can't have 6 and 1 because we can't subtract. This says we're going to subtract them. We can't subtract them and get -1, so that's going to be actually -3 and +2. So if we were to add -3 and +2, we get -1. That's the middle term. So in this case, we do have a factor that reduces here. This factor right here will reduce. So that means my only vertical asymptote is going to happen when we look at this one. So x minus 2 equals 0. So x is equal to 2 is my vertical asymptote. We're going to have a hole at x plus 2 equals 0. So that's the part that factors reduces. So that means it's going to look like x equals -2 is where we're going to have a hole in the graph. And we'll look specifically at the graph and how that looks later on. Now let's look at the third example here. The third example is this. We do have to factor the top. This one may not have a vertical asymptote if the top doesn't factor or reduces. If we have an x minus 5 reducing out, we may not have a vertical asymptote at all. Right now our vertical asymptote is at 5 because that's when that's 0. Let's see, this has got to be 2x and x. There's no other choice. Now 20 could be 20 and 1, which is not likely because of a 3, so I'm going to guess it's the closest ones, 4 and 5. I have choices of 4 and 5, 10 and 2, and 20 and 1. For 20, we need to subtract, and we got to get 3, negative 3. So if I put 4 would not go here, because that means that these are both even, and I could have divided all by 2, and I can't. So I'm going to guess 5 here and 4, and we're going to check. So I get 5x here for the inside and 8x for the outside. Those do subtract and give 3. So I'm going to need this to be negative because of negative 8. So right here I got a negative 8x, and here I have 5x. So this is positive. So they have to have opposite signs because this is negative here. They have to subtract or add if one's negative, one's positive, and give you negative 3. So this is what works out. So this doesn't reduce at all. So I do have a vertical at x minus 5 equals 0. So x equals 5. So I do have a vertical on this one as well. I don't have a hole. It doesn't reduce out. Okay, so that's how we find vertical asymptotes. Now, horizontal asymptotes happen when there's 2 cases here. When the degree in the numerator is less than the degree of the denominator, it's going to be y equals 0. And it's going to be y equals a number when the degree of the numerator and denominator are equal. We have to actually divide here. We have to do long division to figure out what that number is. Okay, so in this first case, it's this one right here, because these are the same. This is a power of 1, this is a power of 1. So what we would have to do horizontal on this problem, let's say we're going to do horizontal, we would have to take this division and figure out what it is. Now we want to just figure out the whole number part. We don't want the remainder, because that's going to be our number here. Our number is the division part, not the remainder, the quotient. Okay, so basically this is 2x plus 2 here. Okay, I don't have to do any more division. This is my horizontal asymptote, y equals 2. Okay, so that's my horizontal asymptote there. Okay, if I have a horizontal asymptote, I do not have an oblique asymptote. Okay, we can have a horizontal or oblique. We can't have both of them happening together. Now, an oblique asymptote happens when the degree, we're only doing linear oblique asymptotes, so it occurs when the numerator degree is 1 more than the denominator degree. Okay, so on these examples I gave you one where we have a horizontal asymptote at 2. This one right here also has a horizontal asymptote at a number. Okay, so if we were to divide this, x squared minus 4 divided into x squared minus x minus 6, that would go in one time because we have x squared minus 4. We don't need to do the division, really. We just need to know what this number is. So my horizontal asymptote here is y equals 1. Now, if we had a degree less, like if I had an x on the top here and x squared on the bottom, that would just be y equals 0. Okay, if I had, let's do this example here. So if I had an example of f of x equals x minus 3 over x squared plus 4, then I'd have a horizontal at y equals 0. I wouldn't have any verticals because this would never equal 0. So no verticals on this one. Just a horizontal. Okay, so on this one, we have an oblique one. So let me move this down. Guess I need to extend this out so I can do some more work. All right, so this one right here has a power 1 more than the denominator. So we are actually going to have to do the division on this to figure out this one doesn't have horizontal, it has oblique. So oblique. Okay, since this is 1 more than this one, that's an oblique. We have to do the division to get the oblique asymptote. So this is done just like the horizontal ones. We do the same division, but we need to know what this quotient is, because that'll give us our oblique asymptote. So if we divide here, we got a 2x here, 2x squared minus 10x. We subtract. Negative changes this to positive 10 and negative 3 is 7x minus 20, so that's going to go in 7, so 7x minus 35. We subtract. We don't care what the remainder is. This is our oblique asymptote, so oblique is going to happen at y equals 2x plus 7. So that is our oblique asymptote. So we have to do long division to find oblique. And we have to do long division to figure out our horizontal as well. Okay, verticals happen when the denominator is 0. A whole happens when we factor and reduce. Horizontals happen in these two cases. And oblique happens if horizontal doesn't happen. Now, there are oblique asymptotes that are curved, but we don't deal with that in this class. So if we have a power that's 2 more on the top and then the bottom, then you're going to have a asymptote that's kind of a curved asymptote. So we're going to not have that in this class though. Okay, so we're going to stick with linear oblique ones. Okay. All right, so now what we're going to do is continue on with finding intercepts and sketching the graph. So we're using the same examples as I had before, but we're going to find the intercepts and then we're going to sketch a graph. We also know the asymptotes from previous problems, right? So we can actually use these to help me graph as well. Okay, so on this one, so the intercepts. So the intercepts happen when we put 0 in for one or 0 in for the other, right? So this one's pretty easy. If you put it in 0, these two things drop out, right? So you have negative 3 over 1. So you have negative 3 as your horizontal asymptote here. Okay, now this one we have to solve. So it's 0 equals 2x minus 3 over x plus 1. Now, if it's a rational function and it equals 0, that just means that the numerator, this part, has to equal 0, because 0 divided by anything except 0 is going to be 0. So that means really we're just solving the equation 2x minus 3 equals 0. So in this case that's x equals 3/2 or 1.5. So that would be my other intercept here. Okay, now we can kind of draw a sketch of this graph. We're just going to draw a little sketch. I don't have graph paper, so we'll do the best we can here. So we know x equals 3/2. So that's 1.5. That's going to be our x-intercept. So it's going to cross right here. Okay. We know it's going to cross at 0, negative 3. So down at negative 3. It's going to cross there. We know that it has 2 asymptotes. So I'm going to go back and look at the asymptotes. Well, actually, I can just look at this. I can tell you the asymptotes. So one of the asymptotes is going to be at 2. The horizontal asymptote is going to be at 2. So we have horizontal asymptote at 2. 1, 2. So we have this asymptote going across here. And we have a vertical at negative 1. So over here at negative 1, we have a vertical asymptote. Okay. So what we have here is we know that this one goes like this on this side. It turns and it goes this way towards the asymptotes. Okay, it doesn't cross this one, it doesn't cross this one. We don't have any points over here. Now, what's going to happen is we need to draw a real graph, we need a couple points over here. So what we would do is we would try some other values in here to get some more points so that we would be able to graph. It's either going to be down here or in this section. We just don't have the graph of that. So I'm going to put in some values that are over here, negative 2 and negative 3, and figure out what they are so that I can complete the graph. So negative 2 is going to be negative 4 minus 3. That's negative 7 over negative 1. So that's going to be as positive 7. Negative 3 is going to be negative 6 minus 3 is negative 9 over negative 2. So that's going to be 4.5. Okay, so I have 2 more points. So this one's going to be way up here at 7. Okay, and then this one's going to be at 4.5, which is way over here. So the graph's going to look like this on this side. And it's going to approach the asymptotes on both of those too. So it's going to look like this. We'd have to expand it out, make it bigger in order to see it. Okay, moving on to this one. The intercepts, 0, comma something. So 0 is going to wipe out all these. You're going to have negative 6 on the top and negative 4 on the bottom. So that's going to be 0, positive 3/2 if we reduce. And then what we want to do is we want to look at where the top is equal to 0, because that's how we find out these values here. We would take this x squared minus x minus 6 equals 0, and we had factored it in the previous side, and that was x minus 3 and x plus 2. So that means I have actually 2 x-intercepts. 3, because 3 minus 3 is 0, and negative 2. Okay, so we have some intercepts, and we know the horizontal asymptote is y equals 1 from the previous thing, and we have a vertical asymptote at x equals 2, and we have a hole at x equals negative 2. Right? That's what we had. Let me go back and look. Make sure I remember that correctly. Okay, hole at negative 2. Oh, that's right. Okay, so if I'm graphing this function now with all that information in general, okay, I'm going to intercepts 3/2, so right here at 0, 3/2, 0, 3/2, I'm going to have 3 and 0 and negative 2 and 0, so that's going to be out here a ways. 3 and 0 and negative 2 and 0. Okay, are going to be those intercepts. I have asymptotes at negative, I have an asymptote at 2, so at 2 right here I'm going to have an asymptote. I'm going to say that's x equals 2, and I'm going to have one at y equals 1, so I have another one at y equals 1 right here. Y equals 1. So it looks like I have a pretty well a good picture of this graph, maybe. Okay, so let's look at this. Okay, did I do 3/2, 0? That's right. Just checking because I'm seeing it cross this axis here, and I'm not sure how that's going to happen on the graph. So I may have to put some more points in to see what it looks like, because usually you're always in one part or the other, and in this case we don't have an asymptote here. Well, let's see if I placed everything in the right spots. 3, 0, that's right. Let's just double check. I factored it the same way as I did over here. 3 and negative 2. 3 and negative 2. Yes, I did factor it the same way. Okay, and I plugged in all of these numbers. Okay. All right, so actually this has got to be the hole. That's right, right. Okay, that's the problem. This is not part of the graph. It's a hole there. I should have seen that already because I said it was at -2. So there's actually a hole here instead of a point. So at that point, we're going to have a hole here. So you have like a little circle where that occurs. Now, the graph is going to cross through these things. So let's try, let's look at some other points. Let's try a couple more points in this thing to see if I can look at this. This is, it's an asymptote, so I'm sure that this side of it looks like this. Okay, I'm sure that that side looks like this. It's this side that's questionable because it looks like it's going to cross the asymptote and go like this. And I'm thinking that it's going to come back up and approach the asymptote because it's supposed to be close to this. So what I'm thinking here is that this one goes this way, comes down and does something down here, but it can't cross the axis because we would have found another intercept, right? So it can't do that because if that was the case, then it would have had another intercept happening. So what I'm guessing here is that it looks like this and comes back up to the asymptote like that. Because 1 is your asymptote, so it's got to approach 1 on the right and on the left. So I'm guessing that this is what occurs here, but we will, let's check a value in this. Okay, so let's take a value and see what happens. This has got to approach this value, but what we want to do is see what happens out here further out. So if we try a value that's a large value, and we get our calculator out and we try a value that's large in this function, let's do that and see what happens. Okay, so plugging it in and seeing what we have here. I'm going to try 10 in this function and see what we get, just to see what happens further out on the thing, see if it's approaching 1. Let's do that. Okay, so all right. So I'm looking at the function. It looks like it's not going to be. So 2, 0 is not on the graph. So what's happening here is that it approaches. It doesn't cross the axis. It looks like this actually. All right. So it doesn't actually cross the axis. Because I tried 10 and it worked. -10. -10 worked on that thing. So there's a hole at that point, and what we were saying here is that this can't be a value. This can't be a value because it's not defined there. So what happens here is that this 2 value should have actually been a little higher. If we were to reduce this, okay, that's what I should have done. I should have reduced this. So if we reduce this function, we would have gotten, let's see, x minus 3 over x minus 2. So that's what the function actually looks like. So if I'd reduced this function, I wouldn't be so confused here. So I guess I should have reduced this. This should have been x minus 3 over x minus 2. So that's just what it reduces to. Okay, so that means that the function looks like this, except it has a hole here. So this wouldn't even be a consideration. I shouldn't add a point there at all because this is really what it reduces to. So 2, 0 is not even close to this function at all. Okay, it should be this function right here, reduced function, and then look at the intercepts and those kind of things. Now it has a hole at 2, negative 2. So if I put in negative 2 here, negative 2 should have been negative 5 over negative 4, which is 1 1/4. So basically this is going to have a hole at negative 2, comma 5/4, which is really comes down and approaches the asymptote there like that. It doesn't cross the asymptote. Okay, that makes more sense. So in this case, don't look at this function for your intercepts. Okay, look at the reduced function for your intercepts. Okay, just knowing that there's going to be a hole at that one point. Okay, so let's move on to this one, the final one here. We're going to look at intercepts here. This one we did factor. Let's say we did factor this one, 2x minus and 5 and x and 4, and this was negative 8. Okay, so this was our factor form. Okay, so our intercepts are going to be 0, negative 20 over negative 5, which is 0, 4. And then our x-intercepts are going to be when this is 0, so that's going to be negative 5 over 2. And 4 minus 4. So these are our 3 intercepts on this function. We then put them in the graph. Oops. And graph them with the other thing. So we have 0, 4. We have 4, 0. And we have negative 5 halves. So that's negative 2.5. Negative 5 halves. Okay, so we have those are our graphs. And we have asymptotes at 5, x equals 5. Okay, so an asymptote at x equals 5. So I have a vertical asymptote here at x equals 5. I have a horizontal asymptote. Oh, actually, this is an oblique asymptote. So we have an oblique asymptote at y equals 2x plus 7. Okay, so an oblique asymptote at y equals 2x plus 7. So that's our oblique asymptote. So we have up here at 7, it'll cross, and it'll have a slope of 2. So it's going to look like this. Okay, so it's going to be like that. It's going to cross down here at negative 7 halves. So negative 7 halves is where it crosses down here. Okay, so we have this graph. So our function is actually going to look like this. It's going to come like this, up through here, turn, and go back down through here. Now, there is another part of the graph way up here that looks the same up here after you're crossing these two values. Okay, so these two things are going to cross up here again, right? So you're going to get another part of it up here. So we'd have to zoom out to see both parts. Okay, so that's how you graph an oblique asymptote. Okay, now we're going to, last part of this is writing a function from information. So let's do that. All right, so we're just going to build a function. We kind of build a function from this. Now the function's built by the vertical intercepts these are okay. These are okay. I typed this in wrong. This is the vertical asymptotes. Vertical asymptotes, because we can't have intercepts and intercepts in this thing. That's not going to work out so well. Okay, so the vertical asymptotes are going to be building our bottom function. So this vertical asymptote at x equals -4 is going to be x plus 4 here. And this one right here is x plus 1. So that builds our denominator. Our vertical asymptotes build our denominator. X-intercepts build our numerator. So this part builds our numerator. So that means that it has to have x minus 1 in it, so that we have a 0 there, and x minus 5 in it, because it has 5. Now the y-intercept is going to tell us what our transformation is. So there's got to be some kind of transformation here. So we need another point to figure out that transformation. So what we do, this is the basic graph built by the asymptotes and the intercepts, or the vertical asymptotes and the x-intercepts. We then plug in the function value of 0, 7 to figure out this constant. Okay, so we would do that. This would be 7. We'd put in zeros for all these values, so that's -1, this is -5, this is 4, and this is 1. So basically we're going to have 7 equals 5a over 4. So it'd be multiplied by 4, which is 28, equals 5a. So a is going to be 28 over 5. So that means our function is 28 x minus 1 x minus 5 over 5 x plus 4 x plus 1. That would be our function. We could multiply this out, but that would be the function that was factored. All right, let's do the same thing, but from a picture. So from a picture, we have the same type of thing here. Now, it doesn't give you any horizontal asymptotes, so that could be it, or it could be something a little bit different depending on what the horizontal asymptotes might be. So in this picture, we have a horizontal asymptote. We have two vertical asymptotes. So we have x equals 4 and x equals -3 for vertical. We know it goes through the point 0, 2, 0, 1 right here, and 2, 0 right there. So it has one thing, and then we have a horizontal asymptote at y equals 0. So this is telling me the numerator and denominator powers have to be the same. And actually the numerator has to be less. Sorry, the numerator has to be less than the denominator. So right now I know from the intercepts that the asymptotes that it's going to be x minus 4 and x plus 3 from these two right here. We know the bottom. Okay, now the top has to be, it crosses through 2, so that means this has to be x plus 2. And we know that there's a horizontal, so that means this power, which is 1, has to be less than this one, which is x squared. Okay. All right, so then what we would do is we would need to find this a value by plugging in the 0.01. So 1 equals a times 2, because we plug 0 in, over -4 and 3. So we're going to have 1 equals 2a over -12. So a is going to be -6. So our function here is -6 x plus 2 over x minus 4 and x plus 3. Okay, but we took all the information off the graph that we would do when we write it out. So it's the same thing, it's just you're taking the information off the graph. Okay, so in this second example, we're going to do the same thing. We're going to take a look at the graph. We'll get some information. So we have two vertical intercepts, or vertical asymptotes, I'm sorry, two red dotted lines. So that's going to give us part of the function right away. That's going to tell us we're going to have x plus 2 down here for this x equals -2 line. This is x equals 4, so we're going to have an x minus 4 here. Okay, so that's what we have there. We have a 0 at 2, 0, but it touches, so that means we're going to have that 0 twice. So that, because if it crosses, we have it once, but if it touches, it's twice. So we're going to have an x minus 2, but we're going to have that twice. So we're going to do that. Now, we know that the intercept is 0, 1/2. So we're going to have to, in order for this to happen, looking at this, we have a horizontal asymptote at 0. So that means the power on the top has to be smaller than the power on the bottom. Well, that means that the power on the bottom right now is x squared, because if you multiply this out, it's x squared. If you multiply that out, it's x squared. So we do not have a horizontal asymptote at 0 right here. So what we're going to have to do here is we're going to have to increase one of these by a power in order for it to have a horizontal asymptote of 0. So that's what we're dealing with here. We have a horizontal asymptote at 0 right here that we have to deal with. So that has to occur. We have to have this power bigger than the other. Now we have to determine which one of these I'm going to raise to a power. So we're going to do one of these two things. We're either going to square this or we're going to square this. Now we need to figure out if the things are in the right areas after we square them. Excuse me. So that means we have to have negative values here, positive and then positive. So what we have to do is we have to try to break it up into categories. Like let's look at the function when it's at -3. What's the function at -3? What's it at? What's it going to be at 0? What's it going to be at 5 or 6 or 7 or 8 or 9 or 10? What's it going to be at 5? Let's say. We need to know this has got to be a positive number, this has got to be a positive number, and this has got to be a negative number, so that we make sure we do that right. Now, let's take a look at if we square this one. Say we square this one. So we're going to have we're going to look at this twice. We're going to look at when x plus 2 is squared, and then we're going to look at it when x minus 4 is squared, and see if we get positive or negative numbers. Now I don't really need to know exactly what the number is. I just need to know whether it's positive or negative. So if we put it in, and let's say this was squared here on this one. So this is the function we're going to evaluate. X minus 4. So we're going to do that. So if we put it in -3, that's going to be positive on the top. And then on the bottom, that's going to be positive here. And the -3 here is going to be negative. So we're going to get negative. So we're okay there, it looks like. Positive and -3 minus 4 is negative. That's good. All right. So we're okay there. Now let's look at 0. 0 is going to give me positive and positive times a negative. So that's going to be a negative number. So this is not going to work out because we're supposed to get positive there. So I can eliminate the square there. Let's try the other one and see if that one works. If we get the right regions there. So x minus 2 squared, and then we're going to do x plus 2 and x minus 4 squared. Okay, so negative is positive on the top. So our goal here again is negative, positive, positive. Okay, let's see what happens here. we have a positive on the top, and we're going to have, let's see, negative 3 gives me negative 1, so that's a negative times a positive because we're squaring it. So that we'll get negative there, that's good. All right, we put in 0, we get positive, positive, positive. So we get positive there, that's good. And then we put in 5. 5 is positive, positive, positive. So we get a positive. So we're actually going to use a square on this one. So then what we want to do is figure out this a value to finish. So to finish this up, we're going to figure out the a value. We're going to stick in a 1/2 and 0. So 1/2 equals a times negative 2 squared, because we're putting in 0, positive 2, and 0 here is going to be 16, because it's negative 4 squared. Okay, so we're going to get over here 4a over 32. That's going to reduce to a over 8 equals 1/2. A, if we cross multiply, 2a equals 8. A is 4. So my equation for this is going to be f of x equals 4, parentheses, x minus 2 squared over x plus 2 and x minus 4 squared. That's my solution for this one. We could check it on Desmos to make sure it works. Okay, this last one here, this is our final one. I just want to put this one in here because it has a hole in it. So we only have one asymptote horizontal, one vertical. So when we do the vertical, the bottom is going to be x plus 1. When we do the horizontal, we have to divide and we have to get 1. So that means this one has to have an x in it because we have to divide and get 1. But we also know that there's a hole at x at 4. So that means that there should have been a factor of x minus 4 on the top and the bottom, because it factored out and gave us this hole. Okay, so that means that, and we also have the point 2, 0 for this intercept, and negative and 0, negative 2. So this intercept here, that means you have to have a root of x minus 2. That tells you that. Okay, now we have the exact same powers, but we have to have an asymptote, horizontal asymptote at 1, which is going to work out here because we have, when we multiply this out, we get an x squared here, and down here we get an x squared also, and then if we divide those two, we're going to get 1. So we will get a horizontal asymptote there. Let's see, we will have an a value, and we need to figure that out from this point. So we're going to take that point and plug it in and see what our a value is. So this looks good so far. We have this 2 because of the intercept. We have these x minus 4s because of the hole. We have the x plus 1 because of this vertical asymptote. And this horizontal asymptote is going to work out because if we multiply, we will get 1 here. So I'm hoping that a is going to be 1. If not, we're going to have to put a value down here too. So let's try this out and see what happens. We're going to plug this point in. So negative 2 equals, because that's the function, right? Function value is negative 2. A times 0, which is negative 2, times negative 4 over 1 times negative 4, right? These drop out. So we're going to get negative 2 equals a times negative 2, which means that a is 1. So our final function for this thing is going to be f of x equals x minus 2, x minus 4, over x plus 1 and x minus 4. X plus 1 and x minus 4. All right, and that's the final example.